Hi everybody. This next section is from 4.3 is on Diagnostics of least squares regression lines. I don't know if this is material I'm going to test you on too much on the midterm or the final, but I think it's something sort of important to go over. So, if you don't get all the homework problems done in this section, it's probably not going to be that big of a deal. So the objectives in the sections will be to compute and interpret the coefficient of determination, perform the original residual analysis on a regression model, and identify influential observations. So the first objective here is about computing and interpreting the coefficient of determination. So the coefficient of determination, or R squared, basically is just the regression coefficients R, the correlation coefficient R that you calculated in 4.1 squared. And it sort of measures the proportion of the total variation in the response variable that is explained by the least squares regression line. The coefficient of determination is between 0 and 1, right? Because remember, R was between -1 and 1, so if you're squaring it, it should be between 0 and 1. If R squared is equal to 0, the line has no explanatory value. And if R squared equals 1, the line explains 100% of the variation in the response variable. So I guess having an R squared value equal to 1, means that the line is a good fit for the data, sort of. I mean, it's a little bit more complicated than that, but you can kind of think of that. So the data to the right are based on a study for drilling rock. So we've seen this before, right? So here's the time to drill a particular depth. So in this case, the x-coordinate is the depth you're drilling to, and then the time to drill is given over here. So if you plot this, if you plot the data here, right, it looks like this. And I think we already determined these, right? The mean for the depth and the time was given by this, and the standard deviation was given by this, and the correlation between time and depth was given by this. And according to the regression analysis we did, right, we had y, or the time in this case, is equal to the y-intercept plus the slope times the depth, or y equals mx plus b. So suppose we were asked to predict the time to drill an additional 5 feet, but we did not know the current depth of the drill. What would be our best guess? So the answer to this case would be the mean time to drill an additional 5 feet would be 6.99 minutes, right, based on our regression equation. Now suppose that we are asked to predict the time to drill an additional 5 feet if the current depth is 160 feet. So in this case, our guess increases from 6.99 minutes to 7.39 minutes based on the knowledge that the drill depth is positively associated with drill time, right? Meaning that the further down you go, the longer it takes to drill. Right, so in this case, you just put 160 in for x, and it gives you 7.39 for the time. And so here's the regression line, right? And so you see there is some difference in, what you get here, right? So the difference here is unexplained by the drill depth, and this is the difference explained by the drill depth, where this line here is the average of the y coordinates. So basically you can think of R squared as explaining the difference here. So the difference between the observed value of the response variable and the mean value of the response variable is called the total deviation. So in this case, right, this would be the total variation from here to here. Okay, so the total variation is composed of the difference of unexplained drill depth and the difference explained by the drill depth. And the difference between the predicted value of the response variable and the mean value of the response variable is called the explained deviation. So, in other words, this distance here is called the explained deviation. So this is sort of what's explained by the equation, but as far as why this is different from what it sort of should be by the predicted value, that's sort of the unexplained value. So again, this is the total variation. If you have a regression line, the total variation is the difference between the average and the actual data point, and then the unexplained deviation is the difference between the average value and the regression lines, right? So remember, the regression line kind of tells you what you should get, right? And then this is the actual value that you do get. So this is sort of explained by the deviation because of the regression line, and this is the unexplained deviation. Again, I'm not going to test you guys too much on this, I don't think, too much, but just to kind of go into this a little bit and explain, you know, when can you decide whether a straight line is a good fit for regression data or not. So if you divide both sides of this equation by the total variation, you basically get this, right? And so r squared turns out to be the explained variation divided by the total variation, right? So this is your r squared. So basically r squared then will be equal to this minus whatever this is, if you rearrange the equation. So one thing to warn you about is to determine the r squared for a linear regression model, simply square the value of the linear correlation coefficient. So like I said, r squared is basically just r squared. Squaring the linear correlation coefficient to obtain the coefficient of determination works only for the least squared regression model, right? So it may not work for, in general, for other models. So something to be aware of. So as far as finding and interpreting the coefficient of determination for drilling data here, because the linear correlation coefficient r is 0.773, then just take r squared, and that will give you about 59.75%. So basically what that means then is about 59.75% of the variability in drilling time is explained by the least squares regression line. So as far as drawing a scatter diagram for each of these data sets, for each data set the variance of y is 17.49. So let's say we want to draw a scatter diagram for each one of these sets, and we've already calculated the variance is given by this, right? So for data set A, that's pretty linear. So 99.99% of the variability in y, the y coordinate, is explained by the least squared regression line. Right, for B, 94.75% or 94.7% of the variability is explained by the least squared regression line. You can see this is still fairly linear. And then for this last data set here, where the data is not linear, right, only about 9.4% of the variability in Y is explained by the least squared regression line, right? So the rest of it is this unexplained value. So objective 2 is to perform a residual analysis on a regression model. So remember, the residual is the difference between the regression line and the actual data points. To determine whether a model is appropriate to describe the relation between the predictor and response variables, right, this is what you want to use it for. And you can also use this to check for outliers. So if you plot the residuals against the predictor variables, not the actual original data points, but the residuals, if there's a discernible pattern such as a curve, the response and predictor variable may not be linearly related, so a straight line may not be a good model. So here a linear model might be appropriate because the residuals are scattered around. Again, this is not the original data. These points represent the distance between the regression line and the actual data. Whereas if you were to plot the residuals here, right, a linear model, a straight line may not be an appropriate model for that data. So here's an example. So in this case, a chemist is weighing radioactive material, and on days 0, right, you have 1,000 grams, and then it starts to decay. So after 7 days, you only have 568.3 grams left. And let's say we want to plot this data, and we want to determine, is this data linear, basically, right? So the linear correlation coefficient in this case is relatively high, and it's negative because the data goes like this. And so if you look at it, you know, the data does look linear, so it would seem like a straight line might be the best fit for the data. But a linear model may not actually be appropriate in this case if you plot the residuals. So, right, if you plot the residuals, you see that you get a curve. So maybe something like a polynomial model or something like that might be a better fit. So if the plot of the residuals against the explanatory variable shows the spread of the residuals increasing or decreasing as the explanatory variable increases, then a strict requirement of the linear model is violated, and this requirement is called constant error variance. And the statistical term for constant error variance is called the homoscedasticity. Again, not anything you guys have to worry about, but maybe something you can impress your family and neighbors with when you go home. So here's the response variable. Here again, we're plotting the residuals, not the actual data here, and you can see it kind of spreads out as you go further here. So a plot of the residuals against the explanatory variable may also reveal outliers, and these values will be easily to identify because the residual lie far from the rest of the plot. So here's an example. And let's say we want to draw a residual plot for the drilling time data that we looked at. So again, this is pretty scattered around, right? A box plot of the residuals for the drilling data looks like this, and so you can see that does kind of show you whether they're outliers or not. Objective 3 here is to identify influential observations. These are observations that may sort of influence your data one way or the other, that if you got rid of them might sort of skew your data one way or the other. So influential observations typically exist when a point is an outlier relative to the values of the explanatory variable. So as an example, let's say that suppose an additional data point is added to the drilling data at a depth of 300 feet if it took 12.49 minutes to drill 5 feet, right? So you get this outlier kind of over here. And so you can see that it can throw off your regression equation quite a bit. As with outliers, influential observations should be removed only if there's justification to do so. So again, you shouldn't automatically remove them, but you might want to go back and look at your data, see if data was entered incorrectly or if you measured something incorrectly. And if you do remove them, you might want to collect more data or use techniques that reduce the influence of influential observations. Okay, well that should wrap up section 4.4. So if you guys have any questions, or 4.3 I mean, so if you guys have any questions about that or anything, let me know. The next section we'll look at is 4.4 and contingency tables and associations. All right, bye.